Hi, let's discuss a little bit this finite state machine adaptation to microcontrollers. That is the kernel idea, the core idea of these P10, P11 and P12 projects before the course ending. So the objective now is simply that one, a systematic and reliable design of projects and real-world applications, avoiding as possible software loops and delays, So let make it a little bit professional. So, we will impose this kind of planning of everything. You see, a finite state machine, even if we have in mind a microcontroller. So this is a kind of a hardware and software diagram where we can in some way mix both worlds, the world of the hardware design that was studied in chapter 2 and the world of software design that is here because this is a computer microprocessor. So let's see. So here we are, the basic idea of a finite state machine, okay? The one that we know from chapter 2. It is based on combinational circuit 2 for calculating the outputs, combinational circuit 1 for calculating the next state to go, the state transitions, and finally the state register that is based on a set of data flip-flops in parallel, so that you have a memory cell to save the current state, and that is the internal state of the machine. And from this internal state, we determine the next state to go and the set of outputs. And that taking into account the input X that are going to modify and establish which is the next state to go and which are the set of outputs for every given state. And then you know as well that there are two special signals, very important, them both. The clear direct to reset the machine and the clock periodic signal that is for synchronizing the next state. So the current state next value is the next state here present in this signal and captured just when you've got clock's active rising edge. That is what we did, and this is what works for all kind of dedicated applications, and it is right for hardware design and VHDL language as well, because it's easy to translate, and for implementing circuits in field programmable gate array and complex PLD. This is what we've been doing in chapter 2, right? So now what we are proposing here is to just promote this adaptation of this very reliable structure to microprocessors. This is what we are proposing here. And to do that, we have to think about the microprocessor as a finite state machine itself in some way. So here you have several boxes, okay? And they are written or drawn in different colors. Some of them are blue, read inputs, write outputs, interrupt event detectors, and some of them are init system, and some of them happens to be in black. And why so? Because in black we have what is called the software domain. Here we rely on variables, RAM memory variables, to calculate through tables or whatever it is that we have to process. So a computer works basically by means of variables, RAM memory content that we just get by using labels, and conveniently we can operate using memory positions all the time, processing any kind of application. So this is what has to be in the kernel of a microprocessor, as usual. But surrounding this kernel, we have a lot of, or some extra functions that, for example, by now what they are for. For example, read inputs are for pulling or reading level sensitive signals like up and down if you are inventing a counter or count enable, or I don't know, night mode, you read, you pull in every computer cycle, in every software cycle, you read the level. So from these levels you generate variables, and from the variables you can determine where to go next, or what kind of variable outputs are going to be written later on, so that you generate the pins that are, for example, LEDs or valves or motors, activators, whatever it is, the output here that or 7-segment displays. So that is the general idea here. You have specific functions to interface the hardware. But this time, because this is a computer, it is okay to go reading or pulling in every computer cycle the level of some signals. Let's imagine that this is P number of signals of this kind, level sensitive. But you know as well that it is extremely important of this idea of being able to move and update the machine that you have in mind, the finite state machine, every clock age. For example, if you are inventing a counter, this is what you want. Every counter's clock be able to generate a new number, and at this specific time, synchronously with this external clock. This is what you like to do in many applications. So how can you adapt that thing into a microprocessor environment? Well, introducing, as well as the read inputs, the interrupt event detector. So some signals are not going to be level sensitive, but edge sensitive, such the clock that we are talking about, or a start button. You like to detect the pulse, and because you have detected the pulse, now the machine can start working. So you see, some signals are like that, edge sensitive. They change the value, whatever it is, from 0 to 1, or doesn't matter, from 1 to 0. There is an event, and this is what you like to detect, this kind of event. And to do that by means of a microcontroller, the best way to do it is by means of interrupt. So you have to have the possibility to interrupt the main program by means of these flags. First of all, you will have, because this event detection means that you have a special hardware, okay? In the same way that when you read inputs or you write outputs, you can do that because you have in the init system the possibility to establish the pin direction, by means of the trees registers that sets the pin direction. Here, if you like to go and detect an event, this edge of a given signal, this happens now. If you like to do that, you have to be able to introduce this hardware, but not for all the pins of the computer ports, but for some of them. For example, the RB0. This is a special input because it is also the external interrupt 0. So that is the case. You have attached to some pins a special hardware for detecting events, and after detecting the events, a hardware flag is set. For example, that one, interrupt or external interrupt 0 flag. And if this hardware flag is set, you can make the program jump to the interrupt service routine. So here is where you are in some way setting a variable flag type. So if this flag is set, you can move the same way what you want, which is the state logic and the output logic. Okay, so this is the adaptation that we will use once and again and many times in most of the applications where we are going to be sensitive to, or we need to be sensitive to, some edges. For example, start. this is when I like to start transmitting data. Now is the time when you have to send to the receiver or to a radio transmitter the serial data. Now is when the timer has to start counting. Now is when the counter has to start accumulating time. Things like that, okay? So this is the important concept that we will manage by interrupts, okay? So you see, you have the same kind of functions that you know very well from the project 9, okay? Init system, read and write, the typical oscillator and reset circuits, but now everything goes around the output logic and state logic. So if in the previous exercise you had a single truth table, and that was the purpose of the previous project P9, solve a truth table by means of reading all the inputs, calculating the table and generating the pins outputs. If you did that in the previous project, now you have the job basically to implement two truth tables, one for calculating the outputs and the other for calculating the next state to go. So that is the adaptation, and probably there is no need of anything else, because for example the block that you see here in the finite state machine, that is the state register, is not necessary now, because current state, you see, current state is a memory variable. Here you have, for example, r bits depending on the way you are coding the finite state machine. So this current state variable or wire that holds the internal state now becomes very well a RAM memory variable, and you have many of them. So let's use a variable in the RAM memory to write the current state, and so by means of this logic we can update. So every time that this state logic works, is executed, you have the new current state calculated, and the new current state is taken into account for calculating the output logics and again for presetting the next state to go. So you see, you can go updating that as in the finite state machine. The same way you can do that thing of updating continuously the current state of the finite state machine. Very well, but this time you see there is logically another big difference. Okay, if this finite state machine update happens here in this in this classic design, every single clock age here in the microprocessor environment, this update happens after each main loop execution. That is the great difference. You see, that is the great difference. So you will in some way update the internal state of the machine every time that you are executing the loop. Okay, that is the great difference, and in some way that is a fundamental difference, because here something that here in the left picture is very clear, the synchronicity, it is in some way lost on the right side. In this picture there is not such a thing as a synchronicity to an external clock in some way. You see, the current state is updated every time that the code executes the state logic. So the faster you execute the state logic without delays, okay, the faster you execute the state logic, well, the faster the machine will be updated, okay? That is the point. And because this is by means of a software loop of instructions, the larger is the instruction set, okay, the larger is the number of instructions included in the software, you see, the larger is the loop, so that is going to impact in the update ratio of the current state. That is the difference. So this updating of the current state, I insist on this, is happening here every time that you are solving a state logic in software, okay? And then there is another possibility that has to be contemplated as well. Naturally, it is the higher the frequency of the internal oscillator that generates the many sequence or the many signals for the microprocessor, you see, the higher the frequency, the faster is executed the loop. So the faster is updated the current state. So that is the way our finite state machine is going to work now. And because of this, you see, we need in some way to apply as usual our clock, our external clock, because it is for something very specific, this clock all the time. Here the clock, it's clearly for, you see, refreshing the current state, right? And here it has to have another idea. Why the clock, for example, is going to be necessary here in this finite state machine? Why we are going to need the clock? Well, because, for example, you like to go sampling an external analog signal at a specific sampling rate. Okay, so the sampling rate is going to be managed by this external clock. External, this time, okay? Or if you are inventing a counter or a timer, you like to go increasing the count number as usual, every external clock rising edge. So you see, in some way, you have the external clock that is for updating the functionality of your real-world application, and the internal clock that is attached to a high-frequency crystal for managing the computer. So sometimes these two clocks are going to generate comprehension problems. But you know, they are very different clocks and everyone has its own purpose. Okay, and sometimes this external clock, okay, the external clock that we will apply since P10, because it's the easiest way to understand how to translate and adapt the classical finite state machine to a microprocessor, you see, later on this external clock may be supplied by internal peripherals like timers. So that is going to be the end. Okay, so P12 will consist of, you see, for example, introducing timers, for example the timer 0, so that from this, you see, microprocessor clock you are going to be able to generate the same signals that now in this P10 introductory lesson are generated externally, to make it easy, because we cannot explain all that thing at the same time. Okay, so that is in some way the panorama. We already know now the read inputs and the write outputs and the way to generate the truth table. Okay, so this is going to be the same, but now another truth table, and those truth tables for very specific purposes as generating a finite state machine. And then some extra functions like the interrupt service routine to interface these new signals that has to be applied to a microprocessor, like a start button, okay? And that's all. So, and this is in some way all the theory that we have here to start designing systematically reliable real-world applications, as you will see in the examples given to you. You see, for example, here you have the possibility to follow and analyze two kind of counters and then a serial data transmitter in this P10. So to finish this introduction, we have to see the same picture that we have discussed now from the software point of view. Okay, exactly what kind of main program we have here to run in this microcontroller. Okay, so to start, there is the reset signal, naturally, the master clear that they call it. So when you apply the power supply and when you click the button master clear, this is nothing but what we know as clear direct. Asynchronously, anytime that you click that signal, you see the microcontroller starts again executing the first instruction in the program memory. So what we have to do in this initialization of the system, one time only after every clear direct pulse is to initialize the system. Naturally, we have to configure, for example, the pins to be inputs and some others to be outputs, and we have to configure as well what kind of interrupts are going to be available here in this application. So that goes first, and this is executed only once. So once the system is already initialized and some pins has a given function, and there is, for example, the possibility to get interruptions, now naturally the operating system of this computer is that simple. Okay, we have an infinite loop. Okay, an infinite loop, while one that is repeated forever. This is what we have in mind, and what exactly we will repeat forever. So as you have imagined here, the finite state machine architecture. This is what is going to be repeated all the time, the same way, as at the higher speed as possible. So read inputs to get, to get level sensitive inputs. Okay, you have some pins that are level sensitive inputs like night mode or up and down or count enable. Such kind of signals are going to be read at the beginning of the loop, so that from these inputs you can very well imagine the state diagram that is able to be, computed. You can get the same state or you can go to the next state depending on this kind of variables, for example. Okay, so you are securing the next state to go, and then immediately you calculate the output logic. That is the function. That is the basic functionality of a finite state machine, as you know very well. Okay, and once the output logic has calculated all the RAM variables that are outputs, what goes next naturally is to write them to the given pins that are connected to LEDs or valves or motors or indicators or sound machines, whatever you have in mind as output of your system. And you do that, you do that calculation once and forever. This is what is the point. That simple and that powerful at the same time, because you can execute this main loop as fast as possible to read as many times as possible per second to make and at the same way. This means that the microprocessor, has a lot of time to implement all the logic if necessary. That is the idea here as well. Okay, and naturally there is the idea attached to this diagram that is also fundamental. How to detect an edge sensitive signal like a clock edge or like a pulse start button, like a start button. How are you going to detect that? As we have organized, anytime running this at higher speed, anytime you can interrupt, like here, click, you interrupt. So if you interrupt the main program, the machine jump to the interrupt service routine program where you have a specific mission. Normally set the variable flag. Okay, for example, the variable start button flag. In this way, when you go back to the main program with this flag set, the state logic can decide what to do, because you know that this kind of arrows, this kind of state transitions depends very much on two conditions or three conditions, or at least one condition. There is always, for example, the bar clock flag to be attended. For many applications you have an external clock or perhaps an internal clock from a peripheral timer that generates clock tickings, and you have to detect them so you can go advancing the machine from one state to the next. This is what we have in mind, and we can do that because after the system has been interrupted, you go back to the main program with this flag set. So in this way you execute the state logic, and the state logic can handle that state transition very well, because there is no difference now between the interrupt detection and the signal that has been read in the main loop. So you see, when the state logic is executed to determine where to go next, you have both the new and updated values of the signals that are read or pulled, okay, in every cycle of the program, and you also have, if that is the case, the flags that has been set in by means of the interrupt service routine. That is the idea. And as well, from this very simple picture, you can finalize this discussion talking about the different colors, why this function has these different colors. Naturally, some of them are attached to hardware and some of them are pure software. So the most important ones, the state logic and output logic, and in the next examples, for example, the data path as well, that's going to be here, the data path for processing whatever you have in mind. You see, those are all software functions that are managed by means of RAM variables. So the data, the information, the stream of bits can be processed very well by a given microprocessor or any other, okay? By an Arduino board, by a microchip, microcontroller, by a Raspberry Pi using Python, doesn't matter. This kernel is the most important one, naturally, and this one is driven by software and is fully compatible between platforms and programming languages, and that is in some way one of the key advantages of programming like this, with this structure. And then what is left, naturally, is the hardware drivers that are attached to every specific microcontroller. So for any one of them, you have to see in which way it is initialized, how to read and how to write the specific pins, because this is something very associated to every single chip, and how to manage the interrupt routine, because this is something that depends on the C compiler or the way the Python indicates how to set the interrupt service routine, so something like this. So that is what we have in mind once and again.